My name is Mfamara K. Damfa. I am a PhD student in the Department of Applied Economics. I'm actually in the Natural Resource Science and Management program. I'm specifically interested in climate change, economics, and policy. And I'm advised by Professor Steve Palaski. As part of my final project for NR 5021, Statistics for Agricultural and Natural Resource Professionals, I've chosen spatial autocorrelation as a topic of interest to explore, to basically understand. And this is the guideline of my presentation. Can I look a little bit into the history of spatial statistics in general, define spatial autocorrelation, look into the causes and assumptions, types and methodology used in detecting spatial autocorrelation in our data. The origin of spatial statistics is traced back to a South African mining engineer, D.W. Krieg, who developed techniques to predict the value of ores within geologic formation. In 1963, Matron further developed a method of interpolation called Kriegen, named after D.W. Krieg. And Kriegen is widely used in GIS today. So Krieg must have done a high contribution, must have laid a very good foundation. No wonder he deserves this credit. The foundation, again, of spatial autocorrelation is based on Tobler's first law of geography, that everything in space is related to everything else, but near things are more related than distant things. Now, in spatial statistics, what spatial autocorrelation literally means is that a variable of interest, variable x, is correlated with itself in space, and that our observations near each other in space have similar values. When the data is spatially autocorrelated, it is possible that we can predict the values of one location based on the known or the sample value from a nearby location, again using Kriegen and other methods. It is important to note that when we are using methods like Kriegen, near points should receive higher weights than faraway points. The way we identify spatial autocorrelation could either be positive or negative. When we see clustering of similar or like values in space, we can say that there is likely to be spatial autocorrelation in our data. When we see clustering of unsimilar or indifferent values, that could be negative spatial autocorrelation. These are assumptions because we have to test for this, because as humans, we tend to see patterns even when they don't occur. Or we tend to see patterns really when they occur, but sometimes they may not even occur, and then we tend to identify patterns, because that is due to our humanness. When there is no spatial autocorrelation in our data, our observations or values of our variable are said to be independently distributed in space, which is referred to as spatial randomness. What causes spatial autocorrelation could be, one, maybe due to poor or bad experimental design, that samples have not been randomly selected. So we have to be careful that when we are doing sampling or designing our experiment, we need to make sure that our samples are randomly selected, because not avoiding that could lead to spatial autocorrelation. But also there is what is referred to as real spatial autocorrelation. Basically, a dependent variable of interest interacts with itself in space due to perhaps some naturally inherent characteristics of that variable. Maybe the variable just perhaps prefer a specific location. It could be because of climatic reasons, it could be other reasons. When we, in class, we're talking about the assumptions of classical statistics, for example, the OLS regression, we assume that our data is randomly distributed. We assume that our observations are independent of one another. And that independence basically implies that the variable is homogeneous, which means there is absence of spatial autocorrelation. In other words, there is spatial randomness in our data. That is what we assume before we do the regression. Violation of the above assumptions basically can lead to spatial autocorrelation, which means that, or which results to a situation where we have inaccurate estimates of our beta coefficients. We tend to have biased results. We have higher beta coefficients, when actually in reality, those values should have been lower. We have exaggerated precisions. In other words, we're having a low or lower standard error, when in reality, our standard error should have been larger. Because when we are claiming that our standard error is small based on the sample size, so when we have a larger sample size and we claim that the sample is randomly distributed and the sample values are independent, when in reality they are not independent. In other words, we are increasing our sample size, reducing our standard error, when actually that is not the case in reality, which is more likely to produce what? A significant test. And we reject the null hypothesis because perhaps our p-value at certain level is significant. So we end up having a significant result or a significant test, when in reality our test is insignificant. So we shouldn't, or we should fail to reject the null hypothesis in that case, but because we assume these independence of our data, having a larger sample size, and then we end up having those significant results, when in reality, like I said, this may not be the case. In spatial autocorrelation, our observations, again, we are interested in the fact that our observations are dependent on each other in space. The likelihood of having high to high values near each other and low to low values near each other. Like I said from the beginning, as humans, we have the natural tendency of identifying patterns in the data. So we have to test these patterns that we claim to be seen statistically. And one of the methods used in detecting spatial autocorrelation is Moran's I statistics. The Moran's I statistics has the global Moran's I statistics and the local Moran's I statistics. In the global one, we basically saw a single measure of identifying overall pattern or spatial pattern in a map. Well, we have to be careful of such patterns, because in that case, we may or may not discover significant level of spatial autocorrelation even when there is such a pattern. So it's important that we test the local Moran's I. That one does a better job in detecting clustering of values. It could be high to high values or low to low values in our locations of interest. The formula for measuring the Moran's I is similar to the formula for the Pearson's correlation. One of the major differences here is that we are interested in variable x value, not x and y. And we calculate these based on the n number of observations on a particular variable of interest. It could be temperature, it could be whatever, at two different locations, location I and j. When we are doing such calculation, we also have to measure spatial proximity, the distance between or among our observations. It's also important to realize or to note that the Moran's I statistics or value interpretation is similar to the Pearson's correlation value interpretation. So when we have values near +1, we see a strong level of positive spatial autocorrelation. When we see values near -1, we said that there is strong level of negative spatial autocorrelation. When we see our values are near 0, we say there is no evidence of spatial dependency or spatial autocorrelation in our data. These are examples of that. In figure E there, on the bottom right, we can see a very strong level of positive spatial autocorrelation compared to figure A on top, where we see a very strong level of negative spatial autocorrelation. So we can see patterns in these two figures, but the patterns are different. So the other one, the first E, we see that similar values, perhaps high and low values are near, high values are near one another and low values are near one another. Whereas the other one, we see the opposite. We see high and low mixed together. But if you compare the two figures there to figure C in the middle, there basically we perhaps might see a pattern as humans, but the pattern that we see is as a result of chance. So that is spatial randomness. We don't basically have any, when we test for that, we have a Moran's I of 0. So basically there is no spatial dependency. In other words, that data is independently distributed in space. Real data examples of spatial autocorrelation here is temperature values for the United States. And again, we can see positive spatial autocorrelation in temperature values around, let's say, the western part of the country. For example, in the Midwest, when we know the temperature value for Wisconsin, we can predict the value for Minnesota. And likewise, the elevation values, the eastern states of the country have very low elevation values. So we can interpolate the elevation values of one state. Knowing the elevation value of one state, we can interpolate the elevation value for another state or for a nearby state. So in the Moran's I calculation, we should also note that these calculation is very sensitive to the weight metrics that we use. So, and there are different weight metrics that are used, but for example, this study did a sensitivity analysis comparing the Moran's I to neighborhood extent for 10 catchment areas in the United States. So as we can see on the figure, as the neighborhood extent increases in meters, we see the Moran's I decreases. That's also important to take note. So weight sensitivity or sensitivity of the Moran's I to the weight metrics that we use. We can do this test in R. Anselm basically have a book on statistics for spatial statistics using R. Is very, very, it has lots of guidelines, very, very easy to apply. So you can follow the codes and apply these things in R. So in conclusion, I just want to note that spatial autocorrelation explains how our variable of interest is correlated or related to itself in space, and perhaps through different locations. So various tests help us to understand the nature of spatial dependency if one exists in our data, whether it is positive or negative. So it is important, again, to note that as humans, we tend to see patterns when actually patterns may or may not exist. So we need to apply a statistical test that will prove to us that yes, in reality, there is a pattern in our data. So I also want to recommend that natural resource conservation biology students should consider testing for spatial autocorrelation in data to avoid biased results, to avoid producing a significant test when in reality there is no significance. I want to thank Professor Rochelle for the wonderful lectures that we have been having in class, and I'm very much happy to say that I have learned a lot from this class, and I look forward to subsequent classes and applying the knowledge I gain. Once again, thank you very much. Have a wonderful holiday.